Well, I'll say good morning to everyone. I hope you all had a happy Thanksgiving and didn't eat too much. So anyway, we're talking about the testing of aspheric surfaces. And we went through the null tests before, and now we'll go through the non-null tests. So not all of these are interferometric. But I'll still say the null test is that even if we have perfect optics, we don't get straight equally spaced fringes. And so there would be no computer-generated hologram or no conventional null optics to remove the asphericity in the system. So looking over this list here, we have 11 items here to talk about. And you know, a nice thing about this course is that most of the items I talk about in the course are things that I have been involved with at some time in my life. But this is sort of the exception here in this list, because the first two on the list, the SCOTS and the scanning Pentaprism test, I have not been involved with either one of these. But I know for the SCOTS, we have students who are experts on this. So who in this class is an expert on SCOTS? Yeah. Who knows a little bit about SCOTS? Ah, okay, 1, 2, good, good. How about the scanning Pentaprism? Any experts in here on that? Ah, okay, good. So I don't have to worry. The two areas that I know least about I have help on. So in a second we'll get to the SCOTS and the scanning Pentaprism. So the goal here in a non-null test is that we won't have to rely upon some null optics, either conventional null optics or CGH, that are made just special for that particular asphere that we're testing. Now there are three kind of general requirements for any interferometric non-null test. The first one, we must get the light back into the interferometer. And so even if it's not an interferometer that we're doing, somehow we have to get the light back into the test setup. And sometimes the slopes of these aspheres are so large that the light will not go back into the test setup. So that's a fundamental problem. If it's an interferometer, we have to be able to resolve the interference fringes. And the other item is, regardless whether it's interferometer or whatever it is, we really have to know the test setup. Because as this aspheric beam propagates along through our test setup, the shape of the aspheric wavefront will change. And so we have to know, so we're measuring something that's a little bit different from what left the optics that we're testing. And so we have to know how the test setup has changed the shape of the wavefront. So this means we're probably going to have to use a Code 5 or Zmax or something to ray trace the system to determine how the wavefront shape has changed. And so that's just, it's such an important item here that I want to mention it again here. You know, in the null test, we create a wavefront to match a test surface. In a non-null test, well, in that case, a reflected wavefront retraces the incident path. In a non-null test, that's not true. And if this reflected wavefront does not retrace the incident wavefront, then we're going to get some of these what we call retrace errors. And this is, you know, I'm emphasizing this because this is an item that people who are testing aspheres often forget. And it's, in some ways, sometimes the hardest part of the whole problem is to determine how your test setup is changing the wavefront that you're testing. So, I mean, we could use a knife edge test, a wire test, or a Ronchi test to test aspheres. But I'm not really going to talk about that. And I don't think these are used much anymore for testing aspheres. The Hartmann test can be used to test aspheres, and that actually can be pretty useful. We've already talked about the Shack-Hartmann, and I'm not going to repeat it here, but we will talk about a test that's pretty closely related to that, the so-called SCOTS test. And several of these tests really will be computerized, and that will certainly simplify the getting good results for the test. So, the SCOTS test. Geez, I finally know what SCOTS stands for here. Software Configurable Optical Test System. So who invented the SCOTS test? Who was the first person to? I think it's Roger Angel is the person I give credit to. Roger Angel is a very, very clever person. I'd say he's a very, very smart person, but he's more than being smart. He is clever. And he comes up with a lot of great ideas. And he nowadays is working in the solar energy business. And he needed a way to test the collector optics for solar energy. And so he came up with what is now known as the SCOTS test. And it's really a lot like the Hartmann test, except it's kind of in reverse, and we'll see that in a minute. It measures slope like the Hartmann test. It's not measuring the wavefront directly, it's measuring the slope. But then you can integrate the results to get back to the wavefront. And from what I'm reading in the literature, they're getting accuracies in a range of 100 to 200 nanoradians. And those of you working on the SCOTS, is that, you agree with those numbers? Or maybe you're doing better than that now, I don't know, for your dissertation. So, I don't know. I put a couple of references up on the website that describes the SCOTS test. And since I said I've never worked with the SCOTS test myself, what I'm talking about here is coming from these references. So if we go back to the Hartmann test, remember what we did, and in the classical Hartmann test, not the Shack-Hartmann, but classical Hartmann, we had a source here, a point source, and here was the optics we're testing. And in front of the optics, we put a screen with small holes in it. And so the light would go up here, and some light would get through the hole to the mirror and come down here. And then we put a photographic plate down here, and sometimes they use 2 photographic plates. But in the classical technique, we used at least 1 photographic plate, and we recorded where these beams came down here and where they intersected the photographic plate. And by knowing the position of the plate and so on, or 2 plates if you use 2 plates, you can, by measuring the position of the spots here, you can measure the slope of the wavefront. And you can compare the slope with what you want and see what the slope errors are here. And these spots can move around in X and in Y, so you're really measuring slopes in both X and Y at a given time. Well, I think what Roger Angel did, and I mean just, it's very, very clever here. He took a computer, and he's going to take a computer like this. It has both a screen and it has a camera in it, okay? And if we say, well, let's just we'll light up one bright spot on the computer screen. And so the light goes out here, and it comes, and it's reflected off here. And here's our camera. And so now with our camera, which could be built into your computer, you're taking a picture of the screen here. And you're seeing where on the screen, or on the mirror I should say, where on the mirror you're testing, is the slope here just right to take light from down here at a position he knows up to the camera and get through the camera lens. And so when he's photographing that, he says, oh, well, that's the spot right there that has just the right angle to get the light from here up there. And if he moves the spot on our display here, then it will be a different location on this mirror that will get the light to our camera lens and forms the image here. And we see where the image is, so we know what spot it is on the mirror. So it's sort of like, going the Hartmann test in reverse. And the beauty, I mean, as I keep saying, Roger is so clever. I mean, it's such a simple setup. This is really can be just a computer screen here and the camera in the computer there. And so you could do a single spot at a time. Of course, that takes a long time then. So you could put a line on here if you want and see where the line, what portions of the line come from different regions on the mirror here. Or you can put sinusoidal fringes on here and image them up here. And then, sinusoidal fringe, that sort of makes me think of phase shifting. And so he could do some phase shifting of these fringes on here and see how they move up here. And from that way, once again, get the slopes. So that's basically it, in my simple-minded thought about it. Now, two of you are probably doing a dissertation on this, so maybe you're going into it a little more detail than what I've explained. So one of you want to tell us a little bit more about the SCOTS? Don't talk at the same time. We'll begin at the back of the room, and then we'll come up here. Okay.
Well, theoretically speaking, this is much. This is very much what you just said.
Uh-huh.
So basically, we take like for the GMT1, we take 16 phase shifting steps per period, and then we take that at one pointing. We unwrap that phase, and then we actually correct for distortion correction, before we get the slope maps. And then we integrate the slope maps to get the surface maps.
Why do you do 16?
For the GMT, with the large optics, that turns out to be more accurate.
Right.
I'm using SCOTS to measure lenses. So my setup is a little bit different, where the screen is on one side, the optic is in the center, and the camera is on the other side.
Okay.
And at this point, I've just tested 1-inch and 2-inch optics, and I'm trying to get the setup, write a alignment plan so that we follow steps by steps and try to get the setup aligned first. I also correct for distortion before I reduce the data.
So can you get results as good as what you get with interferometry? Because that's what I'm reading in these papers. Is that really true?
Well, actually, for the GMT, SCOTS was very, very important, for the high slopes at the edge where interferometry fails. So that's main advantage for SCOTS. And with the LSST now, we're working on LSST, so you cannot get any interferometric measurement at the early stages of lapping. So we're doing the SCOTS test. That's the main test.
I guess that's nice. You can test mirrors. Well, I mean, that's why Roger went to it originally, for testing mirrors that really do not have a great shape at the beginning. And as long as you can test it, then you can keep making the mirrors better and better.
But we do have very good agreement with interferometric test. If we take in our mind the exact position, if we have the exact metrology of the setup, then you can get very close to the interferometric test.
That's great. Well, I had some results here that I took from one of the papers. That's looking at the slopes, so you have to measure both the X and Y slopes and then integrating that to get the surface. And then it looks like they took out what the surface shape was supposed to be, and that's what the departure is. And here's the GMT, where on the right is interferometry, and on the left is the SCOTS. So I think it looks to me like the SCOTS is really a very exciting, quite new technique, and we'll see how it goes with time, and see how how it is used. Do you know other places besides Arizona that uses the SCOTS?
Some place in Germany.
In Germany? Mm-hmm. Mm-hmm.
But they call it detectometry.
Oh, they don't like SCOTS. Okay. What do they call it then?
Detectometry.
Oh, okay. Did they invent it separately, or did they learn about it from the publications?
They invented it separately in the 50s, and it's a very similar technique.
Okay. In the 50s, okay. Well, nothing new, I guess. Well, it is quite similar to the Hartmann test in some ways. Scanning Pentaprism. This has been around forever, I think, but somehow I just never got involved in using it. This, again, is going to measure the slope, and some of you are working on this, so I'll ask you to tell us about it in a minute here, but let me just say a few words here. And so you essentially send a beam through a pentaprism, and you scan that across the surface and look at the reflected beam, or in case of a lens, a transmitted beam. And that way you can measure the angle and determine slope errors. And the nice thing about the pentaprism is that it deviates light by a fixed angle, and so it's not, the measurements are not sensitive to the pentaprism movement itself. This is often used for measuring flat surfaces and for measuring parabolic mirrors. And this shows a result here, which I took from, I guess one of, well, Burge and other people wrote the paper here. And so you send the beam in. We have a couple pentaprisms here that's reflecting the light here, and that would be a stationary one. So that beam comes up here, and you detect the location of that on your CCD. And then this second one here moves around, can swing around, and so send the light down here at different locations. And again, the light will be reflected here, and you'll measure where that spot is as a function of position here, and from that way you map out the slope errors. And this is comparing a pentaprism measurement with a interferometric measurement. So whoever has worked on, who all has worked on pentaprism tests? What?
I've run one, but I've never actually put it together.
Oh, okay. Well, either one of you want to tell us a little bit more about it?
Different than the picture that you showed there. When you use it to test a flat, you can use the reflection coming back through the prism back to an autocollimator, and the reference prism will be one angle, and then you measure relative to that. And, you can do like a rotation where the reference prism will always be at the edge, and then you do scans at different clockings to see what the angles of different parts of a flat mirror are. And it's always returning back through. And one of the big error contributors that you have to do something about is how the prism will wobble going along a rail. So it's a big optomechanical problem, really making sure the prism's actually staying, has its face the same orientation relative to the reference prism as it scans, because otherwise that'll introduce some
Small error.
and if you're measuring small errors in the mirror, then that matters.
So how long has the pentaprism test been around? I first knew about it in the 1960s, so I don't know when it was.
I would like to comment on that. Actually, the beauty of pentaprism is this insensitive to the rotation, so that wobbling actually not from that rotation. It's kind of the height.
Well, the angle, as you change the pentaprism, the angle doesn't change of the beam coming out.
That's the beauty of the
I thought it might be moving to a different location or something is what,
problem.
yeah.
Not a location.
Yeah. But that's the nice thing about the pentaprism is that the angle stays the same. Yeah. Okay. How long? It takes a while to do the test, I would think. And I've seen some results where they used a few pentaprisms, so you're taking a few data points at a time, but it was always a small number of data points. Yeah. Okay, any other comments on pentaprism? Okay. Well, what I'm going to do now is just go through a number of tests pretty fast here for a while, because, you know, lateral shear interferometry, we've talked about this before, so there's not a whole lot more to say. I just want to remind you the advantages is that we can vary the sensitivity by varying the amount of lateral shear. And the disadvantages, well, once again, you're measuring slope. And so you have to have at least 2 measurements with slope in 2 orthogonal directions. And you must know the amount of shear. That's very important to know precisely how much shear you have, as well as the direction of the shear. And as you have larger slopes, it's going to help less. And we'll see that in the next slide here. But the main advantage is you can vary the sensitivity by varying the amount of lateral shear. So kind of get an idea of how does that help you on reducing the number of fringes. I just looked at the one-dimensional case and just say, well, the wavefront goes as a times x to the n. And we're measuring slope. So that's sort of, you know, just take the derivative here. So I have na x to the n minus 1 delta x. And if I take the ratio of the fringes with lateral shear to fringes with a Twyman green, I just take the ratio of this quantity here to this quantity here. And you end up, you get an n times the shear distance over the pupil radius. So the sensitivity goes as a ratio of the shear to the pupil radius. And there's a factor here that goes as the power of the acericity here. So that's what I was saying before, is that it helps less with wavefronts having larger slopes, because n would become larger then. So that gives you a little idea. There are a lot of papers written on use of lateral shear for measurement of A-spheres, and there was a time in my life where I was pretty excited about that, but to be truthful now, I don't think that's it's not a great technique. Radial shear, kind of the same idea here. Advantage, once again, is that we can vary the sensitivity by varying the amount of radial shear. And the disadvantage, well, the shear varies over the pupil, and you have the largest shear at the edge of the pupil, and that's generally where you have the maximum slope. And so what we're saying here is that we're really getting the least amount of help in reducing the number of fringes where we need the most help, where the slope is the largest. And so, again, you can find lots of papers on using radial shear for testing A-spheres, but it's far from my favorite technique, I guess I would say. High density detector arrays. Well, if we're doing an interferometric test, we have to be able to resolve the fringes. And so more detector points, the more fringes we can detect. And from the Shannon sampling theorem, you can think, well, you really need only 2 detectors per fringe. But it's been my experience that you generally need at least 2.5 or 3 per fringe. And part of that is just noise, and really the fact that each detector is averaging over a part of a fringe. And if you have a less than 100% fill factor, so you have a detector spacing, but let's say the detector doesn't cover the entire area. If you just have point detectors, it would work better. Of course, you wouldn't collect much light, but you wouldn't be averaging over a fringe and reducing your signal or your contrast. And as we'll show here in a minute, if I have some additional information about the wavefront being tested, such as the surface height to within a quarter wavelength, or something about the slope. We know something about the slope. We can generally get along working with fewer than 2 detectors per fringe, and we'll show that in just a minute here. Emphasize this point again and again here is that if we're using a high density array to detect high frequency fringes, it means we have this aspheric wavefront going through our test setup, and the test setup is changing the aspheric wavefront. And so knowing the asphericity at the location of the test optic is not enough. We really have to know how the asphericity changes as the beam propagates through the test system. And so we need to have some type of calibration. We need to have some type of ray tracing capability to determine how the test setup changes what we're testing. Well, this idea of not requiring at least 2 detectors per fringe, a technique for getting around that was first described, I think, by John Grevenkamp. And he called this Sub-Nyquist Interferometry. And what he said was, we can get along with fewer than 2 detector elements per fringe if we have some additional information about the wavefront. And this additional information could be simply that the first and second derivatives are continuous. Now, to make this work, we have to have this fill factor less than 1. So if this is showing the spacing of the detectors, we really want detector elements that are smaller than the spacing here. So we have a sparse array. And so when John did this work originally, he took a detector array and he put a mask in front of it with small pinholes. And so he had small detectors compared to the spacing of the detectors. And so if we have detectors that are too large here, and we have a few fringes falling on it, we're essentially averaging over several fringes, and we don't see anything. And so by having a small detector, then we could get the phase at a point here. Now, a small detector, we don't have much light getting to the detector then. When he put his mask with small pinholes in front of his detector, he found he had to have a lot more laser power, which I guess he knew before he tried it. But have any of you in here worked on Sub-Nyquist? Okay. A little bit, okay. So the idea here, I guess maybe we can kind of see it here. We measure the phase here at a few locations here. Let's say here. Let's say these are our phase measurements across here. And the thing is, we know that the slope is continuous. And so the phase at any one of these points could be, it could be whatever the phase is there. It could be that plus 2 pi or that plus 4 pi and so on. So this is a plot that's showing all the possible phase values for that one measurement. And then all the phase values for that measurement. But if you know the phase or the slope is continuous here, you know the slope will go up like this, and it can't come down here. I mean, that's not continuous. So it must kind of go up here. So he uses the fact that the phase, the slope is continuous to unwrap this, and he can have larger than fewer than one detector every or 2 detectors every fringe. Okay. I don't know. John has worked on this for a number of years, and he'll probably disagree with me, but I don't think it has done as well as what he thought it would do. It's kind of interesting, but having it requires this detector with a very small duty cycle, very sparse array, and then you need a lot of power, and they're just kind of, theoretically it's a great technique, but from a practical viewpoint it just probably hasn't done as well as what John had hoped for. I know I was very excited about it the first time he described it to me. Long wavelength interferometry, so, well, we talked about this before. I mean, the advantage here is that you can have a lot of asphericity, but if you go to a long enough wavelength, you still have only a few fringes. So comparing what you would have at a helium neon wavelength of 633 and what you have at CO2 at 10.6, it's just another way of working with a lot more asphericity and still get a small number of fringes that you can analyze, can detect and analyze. So the advantage is you can look at steep wavefronts. The disadvantage is you certainly have a reduced sensitivity, and so reduced accuracy. And I mean, this would be for testing mirror surfaces, not lenses, and not testing visible light lenses anyway. Not testing optics that is intended for use, refractive optics intended for use in the visible. But it can be used for testing of mirrors, and a few people have done it. Disadvantage, another disadvantage is you're working with a wavelength you can't see, which makes it more difficult to do. You can go to two-wavelength holography, which is another technique. I had a lot of fun playing with it one time. And it's a method of using visible light to perform an interferometric test having sensitivity of a test performed using a long wavelength non-visible source. So you can essentially do something like this long wavelength interferometry, but do the work only using visible light. And the idea here, and we'll see the equations in a minute, but the idea is you're going to record a hologram at some wavelength lambda 1, and you're going to reconstruct the hologram using a different wavelength lambda 2. And you're going to get an interferogram that's the same as what you get if you'd used a longer wavelength given by the product of the two wavelengths divided by the difference. And so you can tune your sensitivity of the test by tuning the wavelength difference between making the hologram and reconstructing the hologram. So a lot of different test setups you can do. This is just showing one. Say this is the A-sphere that we're testing, and let's say we make the hologram back here. So we're going to make a hologram using wavelength lambda 1, and we're going to reconstruct it using wavelength lambda 2. Now if we have any chromatic aberration from this lens in the system, we have a problem. Because what we're really doing is we're comparing the interferogram you get at one wavelength with the interferogram you get at a different wavelength. And we're assuming that both interferograms are seeing the same optical path difference. And if the optical path difference is changing because of chromatic aberration, then you're going to get incorrect results here. So let's just see how this works with holography. And we've gone through equivalent wavelengths like this before, but we haven't done it for a hologram. So we're going to measure an OPD. We're going to use a wavelength lambda 1 to make the hologram, a wavelength lambda 2 to reconstruct the hologram. I'm going to give us the flexibility of changing the angle of the reference beam. So we can tip and tilt this mirror. So let's say initially the angle between the two beams is theta 1, and in the reconstruction process, let's say the angle of the reference beam is theta 2. So in making the hologram, we're interfering, assuming unity amplitude, so I don't have to worry about that. We have the wavefront coming from the mirror we're testing, so we can write that as e to the I 2 pi over lambda 1 times the OPD. And so the whole goal here is to measure the OPD. And then we have the tilted reference beam. So we write that as e to the I 2 pi over lambda 1 times the sine of theta 1 times x. So we're recording these amplitudes and squaring it, getting the intensity. And so we get something that goes as 2 plus e to the I, 2 pi over lambda 1, OPD, minus x sine theta 1. And over here we have the complex conjugate of that. So same thing except a minus sign before the I here. So that's used in making the hologram. And then the assumption that we always make here is that the amplitude transmission of the hologram is proportional to the irradiance used to expose a hologram. Always make that assumption. What if that's not the case? Well, the main thing that happens is that the sinusoidal fringes that we're recording will not be recorded as sinusoidal, and we'll end up getting different diffraction orders from the hologram. But if I just look at the first diffraction order, it's going to be essentially the same. And so this, that's a pretty good assumption here if I'm not interested in the higher diffracted orders. So now we're going to illuminate the hologram. So we made the hologram here. Now we're going to change the wavelength, and we're going to illuminate the hologram with the beam coming from what we're testing and the reference beam. And so we illuminate it with e to the I 2 pi over lambda 2 now, second wavelength, times the OPD. So that's the beam from the optics under test. And then the new reference beam is e to the I 2 pi over lambda 2, x sine and theta 2. So we can change the angle of the reference beam used in the illumination here. And if I look at the zero order beam from the test and the diffracted order from the reference beam. So what we're getting out of here now is we're saying that the amplitude transmission of the hologram is some constant here plus something proportional to the irradiance used to expose the hologram. So that was this mess right here. We're illuminating it with this. So what we're seeing is this multiplied times this. And when we do that, we get several beams. But the only beams I'm going to look at here will be the zero order from the test beam and the diffracted order from the reference beam. So the zero order from the test beam, well, that's our test beam right there, e to the I 2 pi over lambda 2 times the OPD. So we multiply that by 2. So that's one beam. Then we have the diffracted order from the reference beam. So that will be, if I take here, I have an e to the I 2 pi over lambda 2 x sine theta, and I'm going to multiply that times this beam right here. Well, no, excuse me, this beam right here, the first one, because I want to get plus OPD. So I'm going to multiply it by that, and so what I get is e to the I 2 pi over lambda 1 OPD, this here, times e to the I 2 pi over lambda 2 x sine theta 2, so that's this beam, e to the I, e to the minus I 2 pi over lambda 1 x sine theta 1. And so that's this right here. Now the other beams coming out of here will leave at different angles if you look at all of them. So these are the only two that are going to leave at about the same angle. And if I can adjust theta 2 to make this term go away, in fact. So that's a lambda 1, lambda 2. So I need to adjust theta 2 a little bit, make it a little bit different from theta 1 to make that go away. But for the time being, I'll leave it in there. So these are the beams that are going to interfere. And so I want to find the irradiance produced by that. And so that's just A plus B cosine times the phase difference. So it's a phase difference between here and here. And so that becomes 2 pi OPD, 1 over lambda 1 minus 1 over lambda 2. So that's coming from the phase difference here, the OPD term. And then I have 2 pi x sine theta 2 over lambda 2 minus sine theta 1 over lambda 1. And if I like, I could write this as 2 pi over lambda equivalent wavelength times the OPD, where 1 over lambda equivalent is 1 over lambda 1 minus 1 over lambda 2. And I could write that then as lambda equivalent is the product divided by the difference. And I like positive wavelengths, so I just say absolute value. So this is the intensity of my interference pattern. And I can vary the tilt in the interference pattern by varying theta 2. And I can get rid of the tilt by making sine theta 2 over lambda 2 equal to sine theta 1 over lambda 1. Or I can have whatever tilt I want and get my OPD here. So we can vary the sensitivity of the test by varying the wavelength difference here. And I can pick whatever sensitivity I want. So advantages, we can get the sensitivity one. The disadvantages, we're finding the difference between these two interferograms, one at wavelength lambda 1 and one at wavelength lambda 2. And any difference between these two interferograms caused by chromatic aberration or air turbulence will introduce errors. And it's worse than that, because these differences will be scaled by the equivalent wavelength. If I have just enough, say, air turbulence to introduce a change of one fringe at wavelength lambda 2, when I analyze my data, I have one fringe error, but I'm saying, well, a fringe corresponds to lambda equivalent. And so even though the air turbulence just caused one fringe error at lambda 2, I'm going to think it's one fringe error at lambda equivalent. So scaled by the ratio lambda equivalent to the individual wavelengths. So that's the real problem here. And it's nice doing this test because you don't have to mess around with light that you can't see, but this is a real problem here. Can be a real problem. Just show a couple of results here. First, we'll look at some equivalent wavelengths. I just put in lines from an argon laser and a helium neon laser and looked at the equivalent wavelengths I could get. And I think the shortest here is 1.66 microns. And I don't know, the longest here is, let's see, it's 47.9. That's might be the longest wavelength. So the idea is that you can really get a wide range of equivalent wavelengths by using different pairs of wavelengths here, making the hologram, reconstructing the hologram. And this is results for testing a mirror. This was interferogram at 4880. Lots of fringes. You can't even see the fringes in here. And then going to the equivalent wavelengths of 6.45. Kind of a reasonable number of fringes to work with. And we can change the tilt, the theta 2, change the tilt of the reference beam in the reconstruction, and vary the amount of tilt in the interferogram. So that was for 6.45. These two are 9.47, 20.22, and 28.5 microns. And if you have a light source where you kind of can continuously change the wavelength, you can really get a huge spread of equivalent wavelengths. And this is just putting the hologram, making the hologram, putting it back in place, and not changing the wavelength at all. So these fringes should be straight, equally spaced. And then we change the wavelength a little bit, and you get equivalent wavelength, 108 microns, 78, so on down here to 40 microns, or 32, 13, 9.5, 7.9, and 7.36. So it's a nice way of changing the sensitivity of the test. It's not limited to testing of optics. This was just an aluminum block where we used really two wavelengths really close together, an equivalent wavelength of 10 millimeters. And one of the students had to bring in a Sesame Street character to contour that as well. So it's kind of interesting. I've had a lot of fun playing with it, but I don't think it's real useful because of the scaling of the errors by the ratio of the equivalent wavelength to the individual wavelengths. Nowadays, you don't. You try to do everything you can in the computer, and so you can really do something pretty much the same thing, where you perform two measurements at lambda 1 and lambda 2, and you subtract the two to get the difference, and you end up with something that's essentially the same for the subtraction in the computer, getting an interferogram that is the same as what you would get if you'd used a much longer equivalent wavelength, given by the product of the wavelengths divided by the differences. Okay. Again, to detect these fringes, you have to have, well, typically, unless you use the Sub-Nyquist technique, you really have to have 2 detector elements per fringe just so you can see the fringes okay. Okay. Going on to something here that really is a lot of fun. What I'll call Moiré interferometry, or projected fringes. And this is a technique that, well, is it useful for testing A-spheres? Probably not. But it's useful for measuring a lot of different objects. And has anyone here done what we're calling projected fringes? It's a pretty... Have you? No, okay. What's that? Similar to? Well, not quite, no. Scott, you said?
It sounds similar to SCOTS.
Well, no, not quite. I mean, there's some similarities, but I'll have to think about just how similar they are. We're not going to measure slope here. We're going to actually measure the shape. So that's one major difference from the SCOT. And we're also going to project the fringes onto the surface. And in SCOTS, you have it some distance away. And so it's a cousin maybe, but not a brother or sister. Okay. It's a test where you're going to vary the sensitivity by changing the spacing of the lines, or sometimes they're fringes instead of lines. Or you can change the sensitivity by, you're going to project these lines onto a surface. You change the angle at which you're projecting the lines on the surface, and or change the angle at which you're viewing the lines. So it's pretty flexible. So we'll go through here and see just how does this work here. It's kind of, I don't know, I think it's, I've had so much fun with this. This is pretty cool. So let's say this red thing here, that's the surface I'm trying to measure the shape of. And if this is a z direction, and y is here, and x is out of the screen here, I can say this surface, I can describe it that z is some function of x and y. And I want to find out what that function is. And what we're going to do is we're going to project lines on the surface. And for my derivation, I'm going to say the spacing of the lines is going to be measured in the y direction. And we're going to say it's d. In some papers, they'll express the spacing as being perpendicular to the lines here. But I'm going to say it's in the direction of y, and it's d. I'm going to say we're projecting these lines here at an angle of alpha, relative to the z-axis here. And we're going to view the lines here at some angle beta relative to the z-axis. And my sign convention is going to be that alpha is positive in the counterclockwise direction, and beta is positive in the clockwise direction. So that reminds, how many years are we going to still remember which way clockwise is and which way counterclockwise is? And that was, I thought of that yesterday when I went over to the rec center to run. And on Monday, let's see, Monday, you were supposed to run counterclockwise, and there were people running clockwise. So I thought maybe they've already forgotten which way clockwise is. I don't know. Anyway, so beta is positive coming down this way, alpha is positive in this way. Okay, so how does this work here? I mean, this I should say, I mean, this technique is older than old. I don't know. And it dates way back long before the early 70s. But this is the first paper I've ever seen that really described this in terms that are very similar to interferometry. So, of course, I love this paper here. Okay, so let's say the surface is z is equal to f of x and y. And we're projecting these lines on this surface, and a straight line, what, y is equal to mx plus b. So I have to get some equation here, y is equal to mx plus b. Well, I'm really talking about z in this direction, so the x is a z here. M is the slope, and so it's z tangent alpha, so that's mx, and plus b. Well, these lines are space d, and the origin here, I go up here to a certain number of lines, and that's a distance nd away, assuming I picked my coordinate system, so one line crosses where the z and the y-axis cross. So my equation describing the straight lines is y is equal to z tangent alpha plus nd. Any questions on that? Because that's the most fundamental part of the whole thing here. Okay, well, z here, I said, well, that's we're intersecting here. That's some function of x and y. So I just put in here that z is f of x and y. So y is f of x and y, tangent alpha plus nd. Okay, that's good. But now, in the McGovern paper, he was really viewing this along the z-axis. But I don't want to restrict myself. I want to view it in some other direction here, and I made beta positive there. So when I see this line intersecting this surface here, and I'm looking in this direction, I think, well, it's really intersecting back here. So I have to put in a little correcting factor for that. And so the y, at where I think the line is intersecting the surface, is at where it actually intersects the surface, f of x, y, tangent alpha plus nd, plus this correction factor due to the fact that I'm viewing it at some angle beta, which is f of x, y, tangent of beta here. So I look here and I think it's intersecting right there. Okay, so this is our equation showing us where we think these lines are intersecting this surface. And when I say lines, I mean you can be projecting lines down here, or I can be projecting interference fringes. I could have two collimated beams interfering, and I have these fringes kind of existing in space, and I see where these intersect that surface. So that's my equation, and I want to rewrite it just a little bit and say, well, y is f of x and y, tangent alpha plus tangent beta plus nd. Okay? So that's my equation then describing where I think these lines are intersecting that surface. So you buy that? Okay. I think I asked you if you buy it or not, because I'm soon going to try to sell you a system that does this. Okay. So, derivation of equivalent wavelength. So we're going to, when I look at these lines intersecting that surface, I mean, when I look at anything with lines, like your shirt, you have interference fringes all over your green shirt there. Okay? I mean, I see interference fringes every place. And so when I look here, these lines intersecting the surface, I think, oh, that looks like interference fringes to me. So let's see. Let's see how we can do that. So we're going to take, oops. I'm going to say, well, let's say we put this surface in a Twyman Green interferometer. And let's say we use a wavelength of lambda. And I'm going to have a plane reference wavefront tilted at some angle. I used gamma here. When do I get a bright fringe? Well, I'm going to get a bright fringe whenever the OPD difference between the two beams is equal to an integer number of wavelengths. And so if I'm illuminating the surface at normal incidence, the OPD I'm going to see is 2f of x and y. And I'm interfering this beam with a plane wave, so that's a y sine gamma. So when this difference here is equal to an integer number of wavelengths, I'll get a bright fringe. And I just, instead of writing m lambda, I'm going to make it minus n. I'll simplify things in a second, but this is just some integer here. It may be positive, it may be negative, I don't know. Doesn't matter. So this is my equation describing the fringes I would get if I put this surface in a Twyman Green. And I can solve for y here. That y is 2f of x and y sine of gamma plus n lambda over sine gamma. So I have this equation for Twyman Green, and I have this equation here for projecting these lines on the surface. And they kind of look, they kind of look similar to me. Okay. And if I compare the two, then I say, well, this 2 over gamma here is sort of like tangent alpha plus tangent beta. Okay, so I'll set 2 over sine gamma equal tangent alpha plus tangent beta. And then I have this n lambda over sine gamma. And I have here an nd. So I have an n equivalent, n times the wavelength. I'll just write that as equivalent wavelength over sine gamma is nd. And I can solve that 2 over sine gamma is 2d over lambda equivalent. So I have some equivalent tilt here, which may or may not be of interest. But the real thing is that I have here, if I just compare these here, I have an equivalent wavelength that's given by 2d over tangent alpha plus tangent beta. Just by looking at these two equations here. So what I have when I project these lines on this surface is something that looks like an interferogram where the equivalent wavelength in a Twyman Green would be 2d over tangent alpha plus tangent beta. So, this looks like an interferogram where the equivalent wavelength depends upon the spacing of these lines, and it depends upon the angle which I project the lines and the angle I view the lines. Now, isn't that kind of neat? So I can vary the sensitivity of this test simply by varying the illumination and viewing angle or the spacing of the lines. Okay? So how can I make a system here? I mean, lots of ways of doing it, but I'll just show one. I could produce, these lines by interfering two beams of light. And I'll have interference fringes. And I'm going to project these interference fringes on whatever it is I'm trying to measure here. And then I'm going to view these fringes down here. And I'm going to see this interferogram. You know. I mean, it looks like an interferogram with some equivalent wavelength. And of course, I like to phase shift everything. So I could phase shift these projected lines here and use my regular phase shifting numbers, or phase shifting equations, to calculate the height variation of the sample. So does this work? And the answer is, it works very well. Here is looking at well, this was a tin can. I don't know why I looked at a tin can, but we did. Probably just had one lying in the lab. And so this was just using this technique here, looking at this can. Now this can be, you have to get light from here down to your camera. So if this is a specular surface, the light may go in the wrong direction. And so this works best with a diffuse surface. So I think this tin can, we painted it white. Okay? And so, contour maps, here's a little profile across it. You get the data in the computer, and you can calculate the slopes. Here's someone's hand. So you just project these lines or these fringes onto a person's hand, take the data, and you get a nice map of the shape of the person's hand. And I remember the name of the student, that was John Meiling. That's John Meiling's hand. Okay? Works pretty well. Amazingly well, in fact. Okay? This is someone's foot. Okay? And so that's the shape of his foot, contour map of his foot, and then just drawing a profile across his foot. So I also know whose foot this is. That's Don Flake's foot. And the story on it, I have to tell this story because this was back in the Wyco days, and we ended up with a big project to measure the shape of feet. And we ended up losing a lot of money on it. So I always have to some way get some joy out of it by talking about what happened anyway. So one day at Wyco, someone just came to the front door. I mean, normally, visitors would always make appointments. This guy didn't make an appointment at all. He just came to the front door, came to the receptionist's desk, and said he had a problem he wanted us to solve. So I said I'd talk to him. And the problem with him, and his problem, is that he wouldn't tell me what the problem was. He had something he wanted to measure, but he was so secret about it, he wouldn't tell me what it was he wanted to measure. So, I figured, what can we do for this guy? I have to get rid of him some way. So I said I'd give him a little tour of the place. My idea, I'd give him a tour. At the end of the tour, I'm going to end up at the front door, and we're going to push him out. He's going to go. So we started a tour, and in one of our labs, we had this system here set up. And he saw this, and he just got so excited about it, and he took his shoe off, and he took his sock off, and the table was just the right height, the beam was coming out there, he just held his foot up here, he said, measure this. And I pressed a button, and the amazing thing is, on the very first try it worked. So I didn't try it a second time, but it worked. And this is the measurement that we did. So then he began to tell us what he really wanted to do. And what he wanted to do was he wanted to have this foot scanner that he could put in podiatrist's office. And so a person would go in to get orthotics instead of, plaster molds and whatever they were using. You would just, some way, with this magic device, you would measure the shape of the person's foot. That would be sent electronically to a lab that would have a milling machine that would mill out your orthotic. They would FedEx it to the person, and the customer would have it the next day. So this sounded pretty exciting to me, and I knew we could do it. And so we started a joint venture with a guy. But there was a fundamental problem here that I should have realized at the beginning. For us, well, we made a foot scanner. I mean, that's it right there. Okay. And so inside of here, we didn't use interference fringes. What we used, we had a little projector, and we had a Ronchi ruling in the projector, and we would project the Ronchi lines onto the person's foot, and then we would defocus it a little bit so the sharp Ronchi lines will kind of look like sinusoidal fringes. And then projector had a little device so we could shift the slide sideways, the Ronchi ruling sideways. So that was our phase shifting. And then we had a little camera in there and a computer connected to it. And we could measure a person's foot very rapidly and very easily. But the problem was, for us to make these and sell them, we had to have a selling price of something like $12,500. And the podiatrists were willing to pay up to $2,500. And so the business model wasn't very good. And so anyway, ended up we lost money, but boy, we had a lot of fun. So anyway, I still have a couple of these foot scanners. And I don't know if I can give you a special deal if you happen to, if you want one. But
Is that the technology they used to do this, or are they still just mold feet?
no, I don't know. The one technique they use is what's so-called a bed of nails, where they have a little thing that look a little bit like nails sticking up, and you step on it, and then from that they have a little transducer measuring how high each nail has been depressed or whatever. This technique actually is used in other areas. It's used in the clothing industry. You can do a very good measurement of your body and have clothes made to really fit you. It's used in a little bit in the electronics industry to measure things like solder bumps and the height of them, contour of them. There's several industries that use the projected lines, projected fringes, but unfortunately not in the foot industry.
What's the measurement accuracy in diamond?
Well, you could get easily 1/100th of a fringe of whatever the fringe spacing is. This is not a nanometer type measurement. It's a micron type measurement. And I think when we were doing the foot, I hate to use English units, but it was like 1/100th of an inch is what we were trying to measure it to. Yes?
You don't have the ability to do like a full three-dimensional?
No, well, we didn't. I mean, we just measured the bottom of the foot. But there are places you can go, and I mean, if you want a statue made of you, there are places you can go. It uses a technique like this.
I was just thinking,
And
so you could like grab a prototype, like a casing around something.
yeah, oh yeah, yeah. And you could do it. You could do it in you don't have to take all the measurements at once. You could rotate the object or whatever and measure it different sides and then stitch them together. Yeah. I mean, there are a lot of applications of this. Unfortunately, it's not testing A-spheres, but a lot of
That technique might be used for like the grinding phase.
Yeah, right. You like to have a diffuse surface because you have to get light back to the camera, and so it would work better in the grinding. In fact, I don't have the results here, but I've taken measurements of surfaces that were ground surface of a lens or a mirror. And that works. It works well, and it gives you the accuracy that you want. Yeah. So it's pretty cool here. Any other questions on this? No takers for my foot scanner, I guess. But anyway. Well, the truth of the matter is, a year ago I cleaned out my garage and I finally threw the last two away. And but I have pictures of this up on my website. And about once a month I'll get an email from someone who wants to buy a foot scanner, but I don't. When I tell them the price, interest goes. What's that? I threw them away. I hate to say it, I did. I know, it was what a mistake that was. They had been pretty much, the parts had been taken out of them, but I probably should have kept it just for my museum or something. I don't know. What's that? Yeah. Could have had it in the lobby here, and you could put in a quarter or something and do a measurement. Yeah. Okay, well, the last item, I think I'm going to stop here. We don't have enough time to really talk about stitching interferograms, but we'll come back to this on Thursday. And then on Thursday, we're going to go on to absolute measurements, which is kind of a interesting, a very interesting subject. So I'll see you Thursday. Don't forget homework in